shattering our sense of scale right now. This very instant, you're standing on a planet that feels enormous. Earth seems vast because it takes hours to fly across it, days to drive between distant cities, and months to explore even a small portion of its landscapes. To us, the ground beneath our feet feels firm, permanent, and unimaginably large. But that sense of scale is nothing more than a trick of perspective. The truth is that Earth, for all its mountains, oceans, and continents, is smaller than a grain of dust compared to the universe that surrounds it. Our entire sense of big comes from human scale experience. Walking from your house to the store feels like a journey. Driving across a state or province feels like an adventure. Flying to another continent takes so long it pushes against the limits of endurance. These references anchor our understanding of distance and size. But as soon as you step beyond Earth, those familiar benchmarks collapse into meaninglessness. Imagine shrinking everything in existence down to a smaller scale. Earth itself would vanish from view before you even left the boundaries of your own galactic neighborhood. Think about the moon, the glowing companion that dominates our night sky. It looks close enough to cover with your thumb, yet it's actually 240,000 miles away. That's like stacking 10 Earths side by side and still not reaching it. Already, your mind is struggling to hold on to the numbers. Our brains evolved to hunt animals, gather food, and navigate landscapes measured in feet and miles, not millions or billions. To us, a million and a billion both just mean really big. But in reality, the difference is staggering. A million seconds equals about 12 days, a billion seconds, 32 years. That's the kind of gulf we're about to cross. If Earth were the size of a marble, the entire solar system would still be smaller than a city block. And that solar system? Just one insignificant dot among hundreds of billions of stars in the Milky Way galaxy. We're about to journey into realms so vast and so strange that your most fundamental ideas of size, distance, and reality will be shattered. We'll encounter objects so dense that a single teaspoon of their matter would weigh more than a mountain. We'll witness collisions that unleash more power in a second than our sun generates in millions of years. We'll confront distances so incomprehensible that even light the universe's speed limit takes longer to cross them than human civilization has existed. The things you consider large, your house, your city, even your country, are about to fade into invisibility. Even Earth itself will soon look oversized compared to what lies ahead. But let's not leap too far just yet. Let's begin where we stand. On the fragile skin of our own planet, every square inch of your body right now is being pressed down by the atmosphere with the weight of nearly 15 pounds. That's like an invisible elephant balanced across your shoulders at all times. You don't notice it because you've lived your entire life inside this invisible ocean of air? Yet, this life-giving blanket is astonishingly thin. If Earth were shrunk to the size of a basketball, the atmosphere would be thinner than a single sheet of paper wrapped around it. Every cloud you've ever seen, every bird that's ever flown, every breath you've ever taken exists inside this impossibly delicate shell. Space officially begins just 62 miles above sea level at the Kármán line. That doesn't sound far. Many of us drive farther than that just to visit relatives. But stack average-sized people on top of each other, and you'd need nearly 60,000 to form a human tower tall enough to touch the edge of space. Picture that, a living skyscraper stretching through the clouds, past where airplanes fly, and beyond where weather exists. Commercial jets, for all their altitude, fly at a mere 6 or 7 miles high. At that height, you would survive for just seconds. Without pressurization, your blood would begin to boil as the air thinned. Mount Everest, the tallest mountain on Earth and a challenge that kills even seasoned climbers, rises just 5.5 miles above sea level. Stack 11 Everests on top of each other, and only then would you breach the boundary of space. Suddenly, that short 62 miles feels like an endless gulf. The International Space Station circles Earth from about 250 miles up. Astronauts on board appear weightless, but it isn't because gravity has vanished. At that altitude, Earth's gravitational pull is still nearly 90% as strong as it is on the ground. The astronauts float because they're falling around Earth at over 17,000 miles per hour so fast that as they fall, Earth curves away beneath them. Their weightlessness is a delicate balance of speed and gravity. Yet for all the drama of reaching orbit, the ISS is closer to Earth's surface than New York is to Washington, D.C. If you could drive straight upward at highway speeds, you'd arrive at the station in less than 3 hours. Only about 600 humans in all of history have ever traveled that far. And the farthest we've gone, the moon, is just a 3-day journey by rocket. But even the moon is still caught in Earth's gravitational grip. In the grand scheme, we've barely taken our first step into the cosmic ocean. Now let's push out farther still. Light from the sun takes just over 8 minutes to reach Earth. In that brief time, it has traveled 93 million miles. To put that in perspective, light could race around Earth's equator 7 times in the same amount of time. That means something extraordinary about the sun's sheer size. Light, the fastest thing in existence, takes more than 4 seconds. Just to cross from one side of the sun to the other, our star could swallow over 1 million Earths and still have room to spare. It accounts for 99.86% of all the mass in the solar system. Everything else, planets, moons, asteroids, and comets combined, makes up barely a fraction of a percent. And yet, for all its power, our sun is unremarkable. Astronomers call it a yellow dwarf, an average star by galactic standards. There are stars so massive and so brilliant that they make our sun look like a flickering ember. And those monsters exist in a galaxy containing hundreds of billions of stars just like it. Our sun is the lighthouse of our tiny world, the furnace that keeps us alive, but compared to what lies beyond, it's little more than a spark. This is only the beginning. Beyond Pluto's frozen orbit, beyond the tenuous edges of our solar system, lies a vastness so incomprehensible that even light struggles to traverse it. And beyond that, the galaxy, the clusters, the cosmic web itself, each step outward will unravel another illusion about size, distance, and permanence. The farther we go, the smaller Earth becomes, until even the sun itself fades into insignificance. We are about to leave home behind, and in doing so, shatter the very idea of big forever. The frozen edge of home, the sun, dominates everything about our existence. It looks like a small, bright disk in the sky, but that illusion is born of distance. In reality, it's a titanic furnace so immense that over 1 million Earths could fit inside, and so powerful that it radiates more energy in a single second than human civilization has used in all of history. Its mass alone accounts for nearly all the matter in the solar system. Everything else, planets, moons, comets, asteroids, is little more than leftover crumbs scattered around the edge of its cosmic feast. Its surface glows at nearly 10,000 degrees Fahrenheit, hot enough to vaporize any substance found on Earth. Yet that's the sun's cool layer. Deeper inside, the core burns at 27 million degrees. In those unimaginable conditions, hydrogen atoms smash together with such force that they fuse into helium. That nuclear fusion converts 4 million tons of matter into pure energy every second, an unbroken firestorm that has raged for over 4 billion years and will continue for billions more. Every sunrise you've ever seen, every warm afternoon, every harvest that's ever fed humanity, all of it is powered by that steady atomic fire. But despite its power, the sun is just an average star. Across the galaxy are giants so large and bright they make our star look like a birthday candle beside a bonfire. Some are so massive they consume themselves in only a few million years, while the sun will last around 10 billion. If our sun suddenly winked out, Earth would freeze solid in days, oceans would turn to ice in weeks, and life would vanish. Yet on the cosmic scale, the sun is a background player, one of hundreds of billions in the Milky Way. Now, travel with me outward, past the planets we know so well. Mercury, a scorched ball of rock closest to the sun. Venus, wrapped in clouds thick enough to crush and cook anything that dares land there. Earth, our fragile oasis. Mars, a frozen desert that once may have flowed with rivers. Beyond them, the gas giants rule. Jupiter so massive it could swallow all the other planets and still hunger for more. Saturn, its delicate rings stretching hundreds of thousands of miles across. Uranus and Neptune, ice giants cloaked in methane blue atmospheres. These worlds, each astonishing in their own right, are still just local neighbors orbiting in the same backyard. At last, we reach Pluto, long ago demoted from planet to dwarf planet. To many, it feels like the edge of our system, the frozen border where the sun's warmth fades into nothing. But Pluto is hardly the end. In truth, it marks only the inner edge of something much larger, the Kuiper Belt, a vast ring of icy debris, stretching billions of miles beyond. Here, frozen worlds tumble in endless night. Their surface is so cold that nitrogen itself becomes rock solid, and beyond even that lies the Oort cloud, the true outer shell of our solar system. It's a spherical swarm of trillions of icy bodies extending halfway to the nearest star. Imagine holding a grain of sand. Now walk more than a mile before you find another grain. That's how far apart the stars really are. The Oort cloud is so distant that light itself takes a year to travel across it. Even the fastest spacecraft humanity has ever built, Voyager 1, launched in 1977 and still speeding away at nearly 40,000 miles per hour, has taken almost half a century to barely graze the edge of this invisible frontier. At its pace, it won't encounter another star for 40,000 years, and yet, even this enormous distance, the edge of our solar system itself, is nothing. It's just the first step into the true cosmic wilderness. From Pluto, the sun looks like nothing more than a bright star. Its heat barely warms the surface to minus 375 degrees Fahrenheit. For all its might, the sun's reach is limited, and the space between stars is so immense that it dwarfs even our solar system's great span. Consider this: light, the fastest thing in the universe, takes just over 8 minutes to travel from the sun to Earth. To Pluto, it takes more than 5 hours. And to the nearest star, Proxima Centauri, it would take 4 years. That's light, the ultimate speed limit. Voyager, for all its momentum, would need tens of thousands of years just to bridge that same gap. The universe has built distances so vast that even beams of light take centuries, millennia, and millions of years to connect one place to another. In the vacuum between stars, there is almost nothing. You could scoop up a cubic foot of interstellar space and, at best, you might capture a single atom of hydrogen. By contrast, a cubic foot of Earth's atmosphere contains trillions upon trillions of atoms. Interstellar space is emptier than any vacuum we could create in a laboratory, emptier than anything our imagination can truly picture. And yet, it is not completely empty. Those few particles drifting silently hint at the web of unseen forces and structures that stretch across the galaxy. Our sun itself, for all its apparent stillness in the sky, is not fixed. It is hurtling through space at over 500,000 miles per hour, dragging its family of planets along as it orbits the galactic center. Even at that blistering speed, it will take 230 million years to complete one trip around the Milky Way. That means when dinosaurs roamed Earth, we were in a completely different part of the galaxy. When humanity first lit fires and painted cave walls, the sun was tens of thousands of light years away from its current position. The stars we see at night are not fixed jewels, but companions in a grand cosmic dance, each one circling, colliding, and drifting across eons. And here's the most humbling part: all of this, every orbit, every frozen world, every icy shell, at the edge of our solar system, is only the beginning. Our home system is nothing more than a dot in a galaxy so immense it defies comprehension. 100,000 light years wide, filled with hundreds of billions of stars, stitched together by gravity into a rotating spiral. We haven't even left our neighborhood, and already the numbers are impossible to hold in the mind. Our spacecraft have barely touched the edge of our own yard, yet the Milky Way stretches on for distances so vast, they make the Oort cloud look like a short walk. In the next step of our journey, we'll leave the solar system behind entirely and plunge into the heart of the galaxy itself, a place of stellar graveyards, cosmic collisions, and black holes so powerful they'd bend space and time. The city of stars. Imagine pulling back from the solar system, zooming farther and farther until even the orbits of Neptune and Pluto shrink to a dot. Beyond the Oort cloud, beyond the faint glow of our sun, we find ourselves adrift in a sea of stars. This is the Milky Way galaxy, our true home. And compared to it, the solar system is a single house lost in a sprawling metropolis of light. The Milky Way contains somewhere between 200 and 400 billion stars. Each one is a sun, many with their own families of planets, moons, and possibly even life. If you tried to count them one star per second, it would take you more than 12,000 years just to finish. And yet, even that enormous number doesn't fully convey the scale. What makes the Milky Way so overwhelming is not just how many stars it contains, but how far apart they are. Our galaxy is a rotating disk, about 100,000 light-years across. That means a beam of light traveling at 670 million miles per hour would need 100,000 years just to cross from one side to the other. Voyager 1, the fastest spacecraft humanity has ever launched, would need over 1 billion years to make the same trip. Long before it even approached the far edge, Earth would be gone, the sun would be a cold ember, and the galaxy itself would have transformed into something unrecognizable. And here's the astonishing part: for all its vastness, the Milky Way is still just one galaxy among trillions. But let's not leap too far. First, we must understand the enormity of our own galactic city. Our solar system orbits the galaxy's center at a blistering 515,000 miles per hour. At that speed, we travel 140 miles every second. Yet, even moving that fast, it will take us 230 million years to complete a single orbit. The last time the sun was in this position, dinosaurs still ruled the Earth. The next time we arrive here again, life on Earth may be unrecognizable, if Earth even survives. At the center of the Milky Way lies a monster, a supermassive black hole called Sagittarius A*, containing the mass of 4 million suns crushed into a region smaller than the orbit of Mercury. This invisible engine warps everything around it. Stars whip around the black hole at incredible speeds, some completing entire orbits in just 16 years. Imagine something so massive that time itself slows in its presence. The gravity here is so intense that even light cannot escape. From our position in the galaxy's suburbs, about 26,000 light-years away, we cannot see the black hole directly. Clouds of gas and dust obscure our view. But if you could clear that cosmic fog, the galactic core would blaze in the night sky, brighter than the full moon. Billions of stars packed into a compact region would turn darkness into a permanent twilight. The center of the Milky Way is a place of chaos, stars forming, exploding, colliding, and vanishing into the maw of Sagittarius A, and our galaxy is far from static. Even now, it is devouring smaller galaxies. Streams of stars, stretched and shredded like ribbons, wrap around us, remnants of ancient galactic feasts. Over billions of years, the Milky Way has grown fat on its neighbors, pulling them apart and scattering their stars across its spiral arms. We are not watching a finished masterpiece, but a work in progress, painted slowly by gravity over cosmic time. Among the Milky Way's hundreds of billions of stars are some that defy belief. Take UY Scuti, one of the largest known. Place it where our sun sits, and it would engulf Mercury, Venus, Earth, Mars, and extend well beyond Jupiter's orbit. Light fast enough to circle Earth in a fraction of a second would need 9 hours to travel around this single star. Driving at highway speeds, it would take you 9 million years just to complete one lap around its surface. And yet UY Scuti is not the most massive star we know. That title belongs to giants in the R136 cluster stars up to 300 times the mass of the sun. These stellar titans burn so furiously that they live only a few million years, a cosmic blink compared to the sun's 10 billion year lifespan. When they die, they do so violently, exploding as hypernovas and releasing more energy in a moment than our sun will radiate across its entire lifetime. But these giants are rare. Most stars in the Milky Way are small red dwarfs, faint and long-lived. Some will continue burning for trillions of years long after our galaxy has changed beyond recognition. If life exists elsewhere in the Milky Way, it may be orbiting one of these dim, quiet suns, thriving in stability while our own star eventually flares and dies. The Milky Way is not just stars, of course. It's also gas, dust, and invisible dark. Matter, great clouds of gas stretch across light years, serving as nurseries where new stars ignite. Dust veils portions of the sky, blocking our view with its cosmic smoke. And dark matter 5 times more abundant than all visible matter wraps around the galaxy like a ghostly halo. Though invisible, its gravity holds the Milky Way together. Without it, our galaxy's stars would fly apart, seen edge on the Milky Way appears as a glowing band of light arcing across the night sky. Ancient civilizations looked up at it in awe, weaving myths and legends. Today we understand it for what it is, the combined glow of billions of distant suns, woven into a vast spiral structure. Our own position is in the Orion Arm, a minor spur located between 2 larger arms. We are not at the center of anything, but at the edge of a vast whirlpool of stars, a quiet neighborhood far from the galaxy's bustling core. And here's a humbling thought. Everything we've ever known, every human who has ever lived, every story ever told, every civilization that has risen and fallen has happened inside this tiny corner of one galaxy. The universe beyond holds countless more, but before we step outside the Milky Way, let's pause to absorb its immensity. 100,000 light years across, hundreds of billions of stars, a central black hole, endless cycles of birth and death, rivers of stars from consumed galaxies, clouds of gas birthing new suns. All of it bound together by gravity, moving in harmony through the void, and yet, compared to what lies beyond, the Milky Way itself is just one island in an infinite ocean. Ahead of us are galaxy clusters, superclusters, and cosmic structures. So vast, they bend the limits of imagination. Our journey into the universe has barely begun. Monsters, corpses, and cosmic violence, the Milky Way dazzles with its hundreds of billions of stars. But not all stars are created equal. Some shine faintly and live for trillions of years. Others flare like titans and die young, their deaths, reshaping the universe. If the galaxy is a city of stars, then its streets are filled with both gentle, flickering candles and roaring infernos. And among them lurk corpses so dense, so strange, they seem more like riddles of physics than natural objects. Take UI Scuti, for example. It is not the most massive star we know, but it is gargantuan in size. If placed where our sun sits, UI Scuddy's outer surface would extend beyond the orbit of Jupiter. Imagine Earth circling inside such a star, swallowed whole by its vast, bloated atmosphere. A beam of light, normally fast enough to circle Earth in a fraction of a second, would take 9 full hours just to travel around its circumference. Drive around it at highway speed, and the trip would take 9 million years, despite its enormous size. UI Scuti isn't especially heavy. In fact, it contains only about 30 times more mass than the Sun. Its outer layers are so diffuse they are almost like a vacuum. If you could somehow stand inside its atmosphere on a floating platform, you might not even realize you were inside a star at all. That's how thin and ghostly these giants can be, and yet UI Scuti isn't the true heavyweight champion. That title goes to stars in the R136 cluster, some with masses 200 to 300 times that of the Sun. These monsters burn their nuclear fuel so furiously that their lives last only a few million years, a blink of an eye compared to the Sun's 10 billion years. Their light outshines entire galaxies, and when they die, they explode in hypernova's cosmic detonations. So violent they can be seen across billions of light years. But what comes after such violent ends is even more fascinating. When a massive star runs out of fuel, gravity takes over. Its core collapses and the outer layers are blasted into space in a supernova. What remains can be one of the strangest objects in existence. A neutron star? Picture something with more mass than the Sun, squeezed into a sphere just 12 miles across, smaller than Manhattan. In that collapse, protons and electrons are forced together, creating a star made almost entirely of neutrons. The density is unimaginable. A teaspoon of Neutron star matter would weigh billions of tons more than every car and truck on Earth combined. Hold a sugar cube of it in your hand, and it would weigh as much as a mountain. On the surface of a neutron star, gravity is 200 billion times stronger than Earth's. Drop a marshmallow there, and it would strike the surface with the force of 1,000 hydrogen bombs. NASA once used this thought experiment to illustrate the absurdity of these conditions. In reality, any object would be crushed and vaporized instantly, long before reaching the surface, but neutron stars are more than just dense balls of matter. Many of them spin at incredible speeds. Some rotate hundreds of times per second, their equators moving at a fraction of the speed of light. These spinning corpses are called pulsars because their powerful magnetic fields funnel energy into beams of radiation that sweep across space like cosmic lighthouses. From Earth, we detect them as regular pulses of radio waves so precise that some pulsars keep time better than our most advanced atomic clocks, and then there are magnetars, the rarest, most extreme version of neutron stars. Their magnetic fields are 1,000 times stronger than those of regular neutron stars. To put that in perspective, a magnetar could erase every credit card on Earth from a distance of 100,000 miles. The energy contained in its magnetic field could power human civilization for 1 billion years. These are cosmic engines beyond anything we can build, and yet they exist naturally in the universe. As violent as neutron stars are, they pale beside what happens when two of them collide. For millions of years, binary neutron stars spiral closer together, losing energy through gravitational waves ripples in the fabric of space-time itself. Eventually, they merge in a cataclysm called a kilonova. On August 17, 2017, humanity witnessed one of these collisions. Gravitational wave detectors on Earth registered the vibration of space-time from a merger 130 million light-years away. Telescopes around the world swiveled to watch the aftermath. For a few days, that single event outshone its entire host galaxy. The explosion created conditions hotter and denser than anything since the Big Bang. In seconds, it forged heavy elements gold, platinum, uranium, and hurled them into space. The jewelry on your finger, the platinum in electronics, the uranium. In reactors, all of it was born in such cosmic collisions. Billions of years ago, the kilonova also confirmed Einstein's predictions about gravity. Gravitational waves traveled across 130 million light-years without losing their information, proving that space-time itself ripples like water when disturbed by colossal events. The collision also unleashed a gamma-ray burst and eruption, so energetic that, had it happened nearby, it could have stripped Earth's atmosphere. Fortunately, it was far enough away to serve only as a spectacle of cosmic violence. Even more extreme than neutron stars are black holes, the ultimate endgame of massive stars. When gravity becomes so powerful that nothing, not even light, can escape, a black hole is born. But black holes deserve an entire chapter of their own. For now, imagine the death of stars as the universe's recycling program. Supernovas and kilonovas don't just destroy, they create. They scatter elements into space, seeding future stars, planets, and life itself. Think of it this way. Every atom of calcium in your bones, every atom of iron in your blood, every atom of gold in your jewelry was forged in the heart of a dying star or the collision of neutron stars. You are, quite literally, made of stardust, but as we move deeper into this journey, the violence only escalates. Dark matter, invisible yet 5 times more abundant than everything we can see, holds galaxies together. Dark energy, an even stranger force, is tearing the universe apart. And at the centers of galaxies, supermassive black holes consume stars whole, blasting out energy that dwarfs entire galaxies. The Milky Way has already shown us wonders beyond comprehension: giant stars that dwarf our sun, stellar corpses that bend physics, and cosmic explosions that forge the very elements of life. But compared to what lies ahead, even neutron stars and supernovas are only the beginning. The invisible universe. So far, we've journeyed through the blazing hearts of stars, witnessed their violent deaths, and seen the stellar corpses they leave behind. But as strange and powerful as these objects are, they represent only a fraction of what actually exists. Most of the universe is not stars, planets, or gas. In fact, everything you can see, every galaxy, every nebula, every particle of dust makes up less than 5% of the cosmos. The rest is hidden. Dark matter and dark energy dominate the universe, shaping its structure and its fate. Together, they account for over 95% of everything, yet we cannot see or touch them. They reveal themselves only through their effects. And those effects are staggering. Let's begin with dark matter. Astronomers first suspected its existence in the 20th century when they noticed galaxies behaving in ways that defied physics. Based on visible matter alone, stars and gas galaxies should have spun themselves apart. The outer stars should orbit much more slowly than those near the center, just as the outer planets in our solar system move slower than the inner ones. But when astronomers measured galactic rotation curves, they were stunned. Stars on the outskirts moved just as fast as those near the middle. Something unseen had to be adding extra gravity, holding the galaxies together. That something is dark matter. Unlike ordinary matter, dark matter does not emit light, absorb light, or interact with electromagnetic forces. It passes through ordinary matter as if it doesn't exist. Right now, billions of dark matter particles are streaming through your body every second, leaving no trace. And yet, their collective gravity is strong enough to bind galaxies and shape the universe. Computer simulations of the early cosmos show that dark matter clumped together first, creating invisible scaffolds. Ordinary matter then fell into these dark matter halos, forming stars, galaxies, and clusters. Without dark matter, there would be no galaxies, no planets, no life. It is the silent architect of everything we see. Our own Milky Way sits inside a vast halo of dark matter that extends far beyond the galaxy's visible edge. This invisible structure contains 10 times more mass than all of our stars combined. Without it, the Milky Way would have flown apart billions of years ago. Astronomer Vera Rubin's pioneering work in the 1970s confirmed this strange reality, revealing that dark matter is not just an oddity of our galaxy but a universal phenomenon. Every galaxy everywhere requires invisible mass to explain its motion, and yet, despite decades of searching, we still don't know what dark matter is. Leading theories suggest exotic particles, WIMPs, or weakly interacting massive particles that were born in the first moments after the Big Bang. Others propose axions, sterile neutrinos, or even tiny black holes formed in the universe's infancy. Detectors bury deep underground wait in silence, shielded from cosmic rays, hoping for a rare collision between dark matter and ordinary atoms. But so far none have revealed themselves. Dark matter remains a ghost. If dark matter is the universe's skeleton, dark energy is something even stranger, the force driving the universe apart. In the late 1990s, astronomers studying distant supernovas made a shocking discovery. Instead of slowing down under the pull of gravity, the expansion of the universe was accelerating. Something unseen was pushing galaxies away from each other faster and faster. That something is what we now call dark energy. Dark energy makes up about 68% of the universe. Unlike matter, it doesn't clump together. Instead, it is spread evenly throughout space, exerting a repulsive force like anti-gravity. It doesn't matter whether you're in the middle of a galaxy cluster or floating in empty space. Every cubic meter of the universe contains the same small but relentless dose of dark energy. And though the amount in any one place is tiny, multiplied by the vastness of space, it becomes overwhelming. 5 billion years ago, gravity was still winning, slowing the universe's expansion. But as galaxies drifted farther apart, dark energy began to dominate. Since then, it has been pushing the cosmos outward at an ever-increasing rate. Galaxies that are close together like the Milky Way and Andromeda will still collide, because gravity can overpower dark energy on small scales. But beyond our local group, galaxies are already slipping away, moving faster than we can ever hope to reach them, even at the speed of light. This accelerating expansion has profound consequences. Right now, we can observe galaxies up to 46 billion light-years away. But in the far future, even nearby galaxies will disappear beyond our cosmic horizon. The night sky will grow emptier and darker. In trillions of years, distant galaxies will vanish from view entirely, leaving future observers trapped in isolated bubbles of stars, cut off from the rest of the universe. In this distant future, the cosmos will grow colder and darker as stars burn out and black holes slowly evaporate. The ultimate fate of the universe depends on the true nature of dark energy. If it remains constant, the universe will expand forever, approaching maximum entropy, a heat death where nothing happens because everything is spread too thin. If dark energy changes over time, even stranger fates are possible. A big rip, where expansion eventually tears galaxies, stars, planets, and even atoms apart. Or perhaps dark energy could reverse, pulling the universe back into a catastrophic big crunch. For now, we don't know. Dark energy is even more mysterious than dark matter. It might be vacuum energy, the quantum fluctuations of empty space. It might be a dynamic field, something physicists call quintessence. Or it might be a property of space-time itself, baked into the very fabric of reality. Whatever it is, it will determine the fate of everything. So think about this: all the galaxies, stars, and planets we see, all the things we consider the universe, are really just decorations on a much larger stage. Dark matter holds the scaffolding together. Dark energy drives the expansion outward. They are the true rulers of the cosmos. And yet, compared to what comes next, even these invisible forces are just part of the backdrop. Beyond galaxies and clusters lie the largest structures in the universe, cosmic webs stretching for billions of light years, walls of galaxies so vast they challenge the very theories of cosmic evolution. The universe is about to show us its grand architecture. The cosmic web. Now, we've seen how stars live and die, how dark matter binds galaxies, and how dark energy pushes the universe apart. But to truly grasp the scale of everything, we have to zoom out even farther, far beyond individual stars, beyond galaxies themselves, to the very framework of the cosmos. Out here, we discover that the universe has an architecture, a grand design woven across billions of light years. Galaxies are not scattered randomly. They gather in clusters, cosmic cities containing hundreds, sometimes thousands of galaxies bound together by gravity. These clusters can span millions of light years across and weigh as much as a quadrillion suns. The Milky Way belongs to a small local group of about 80 galaxies, which in turn is part of the Virgo cluster, a sprawling assembly stretching tens of millions of light years wide. But clusters themselves are just building blocks of something larger. Superclusters. These are immense regions where thousands of galaxies gather into sprawling structures hundreds of millions of light years across. Our local group and the Virgo cluster are part of a giant supercluster called Laniakea Hawaiian for immeasurable heaven. Laniakea contains more than 100,000 galaxies spread across 500 million light years. Even with its immensity, it represents just one patch in a cosmic quilt. Superclusters don't exist in isolation. They're connected by invisible threads of matter that stretch across the universe, the cosmic web. Imagine a spider's web spun on an impossible scale, with galaxies and clusters strung along its filaments. These filaments stretch hundreds of millions of light years, connecting superclusters like highways of matter. In between are cosmic voids, enormous regions almost empty of galaxies, one of the largest known voids. The Boat's void is 330 million light years across. If the Milky Way were in its center, we might not have discovered other galaxies until the last century. Voids like this make up much of the universe, with galaxies existing mostly along the thin filaments between them. On the largest scales, the universe looks foamy, vast, empty bubbles surrounded by delicate walls of matter, with luminous galaxies marking where the filaments intersect. And then there are the giants, the structures so large they defy our models of cosmic evolution. The Sloan Great Wall, discovered in 2003, stretches 1.37 billion light-years across. The South Pole Wall, discovered in 2019, is even larger, 1.4 billion light-years wide. And towering above them all is the Hercules Corona Borealis Great Wall. the largest known structure in the observable universe. This cosmic wall spans 10 billion light-years. Light, the fastest thing in the universe, would take 10 billion years to cross it nearly. The entire age of the universe itself. The very existence of these structures is a problem. According to current theories, there hasn't been enough time since the Big Bang for gravity to assemble something that large. They shouldn't exist, yet they do. Their discovery forces cosmologists to rethink the limits of structure formation and challenges the principle that, on the largest scales, the universe should look uniform. What's even stranger is how we detect them. These walls are mapped not only by galaxies, but also by gamma-ray bursts, the brilliant explosions that occur when massive stars collapse into black holes. By plotting where these bursts appear, astronomers can trace the outlines of hidden structures billions of light-years away. It's like lighting candles in a dark cathedral and slowly realizing the cathedral is bigger than you ever imagined. The cosmic web is not static. Matter flows along the filaments, pulled by gravity toward clusters at their intersections. Galaxies move like cars on highways, drifting toward the largest nodes where superclusters form. This cosmic traffic has been happening for over 13 billion years and continues today. Our Milky Way, for example, is moving toward the Great Attractor, a mysterious region of space so massive that it bends the motion of entire galaxy clusters around it. Gas also flows through the filaments, heated to millions of degrees. Recent X-ray observations revealed that these filaments contain most of the universe's missing matter. Ordinary atoms that escape detection for decades because they are too diffuse to see with optical telescopes. Hidden between galaxies, this hot plasma glows faintly in X-rays, filling the spaces of the cosmic web like blood flowing through veins. When you step back far enough, the universe resembles something eerily familiar. The cosmic web's pattern of filaments and voids looks strikingly like the neural network of a brain. Billions of galaxies linked in webs of matter mirror billions of neurons linked in webs of thought. It's a coincidence, of course, but it's also a reminder that patterns repeat across scales, from the microscopic to the cosmic dot, and yet, even these vast webs may not represent the largest possible structures. Some scientists propose the existence of supervoids regions billions of light-years wide, where matter is almost absent. One such feature, known as the cold spot in the cosmic microwave background, might be an 18 billion light-year wide void. If confirmed, it would dwarf even the Great Wall and force a radical rethinking of cosmic structure itself. Here's the humbling truth. The structures we can map superclusters, walls, filaments represent only the observable universe. Beyond our horizon, there may be even larger patterns, repeating endlessly across distances we will never reach. For all we know, the Hercules Corona Borealis Great Wall is just one panel in an unimaginably larger tapestry. Our entire supercluster, Laniakea, would appear as just a dot when placed next to these great walls. And the Milky Way, our home galaxy, with its billions of stars, would be indistinguishable from a grain of sand. When we talk about large in human terms, mountains, oceans, continents, we are playing with toys compared to the architecture of the cosmos. Think about it. The universe contains walls of galaxies billions of light-years wide, voids so empty they stretch across cosmic time, and filaments so long they connect clusters like threads in a web. This is the true stage on which the drama of existence unfolds, but even this stage may not be the final one. Beyond the web lies something stranger still, the question of the universe's shape, its boundaries, and whether it is infinite or just one bubble in a vast multiverse. And that's where our journey leads next. The edge of Forever Web crossed vast distances, from Earth to the Moon, from the solar system to the Milky Way, from galaxies to the colossal walls of the cosmic web. Each step shattered our old sense of scale, forcing us to redefine what large even means. But now we've reached the ultimate question. Does the universe have an edge? And if it does, what lies beyond? Astronomers speak of the observable universe, the region of space from which light has had time to reach. US since the Big Bang, because the universe is 13.8 billion years old. You might think its radius is 13.8 billion light years, but that's not quite true. While light has been traveling toward us for 13.8 billion years, space itself has been stretching all the while. As a result, the edge of the observable universe is about 46 billion light years away in every direction. That makes the observable universe nearly 93 billion light years across. Everything we can see, the billions of galaxies, the colossal cosmic webs, the great walls and voids, all of it exists within this spherical bubble centered on Earth. Not because we are special, but because that's the distance light has had time to travel. Every observer, anywhere in the universe, would have their own bubble centered on themselves. But what lies beyond this horizon? The most likely answer: more universe. Galaxies, clusters, filaments, and voids continue, far beyond what our telescopes can see. They don't simply stop at 46 billion light years. The cosmos extends outward perhaps infinitely. But because light from those regions has not had enough time to reach us, they are forever hidden. The observable universe is not the whole universe. It's just the part we can access, like a ship lost at sea with only the horizon in view. And here's the humbling part: as the universe expands, more and more galaxies slip beyond that horizon. Dark energy pushes them away faster than light can catch up. Today, we can observe galaxies 46 billion light years away. In the distant future, that number will shrink. Not because the universe is getting smaller, but because more galaxies are being carried out of sight. Eventually, only our local group of galaxies will remain visible. Everything else will vanish into darkness. Future astronomers will look up and see only a lonely sky, never knowing the universe was once filled with galaxies. But perhaps the most mind-bending question is not about what lies beyond our horizon, but about what came before it. What happened at the very beginning? According to the Big Bang model, the universe began as an incredibly hot, dense state and has been expanding ever since. But in the 1980s, physicists proposed an idea called cosmic inflation, a brief period, less than a trillionth of a second after the Big Bang, when the universe expanded faster than the speed of light. In that instant, space itself ballooned by an incomprehensible factor, smoothing out irregularities and setting the stage for the cosmos we see today. Inflation explains why the universe looks so uniform in every direction and why the cosmic microwave background, the faint afterglow of the Big Bang, appears nearly the same everywhere we look. But inflation has an even stranger implication. If space can expand that way once, it might do so repeatedly. Inflation could be eternal, creating not one universe, but an infinite sea of bubble universes, each with its own laws of physics. This is the multiverse hypothesis, a concept as staggering as it is controversial. In some universes, gravity might be stronger, tearing stars apart before they form. In others, the fundamental constants of physics might differ, preventing chemistry and life altogether. We exist in a universe where conditions just happen to allow stars, planets, and people. Whether that's luck, inevitability, or evidence of infinite variation, no one yet knows. The multiverse may never be directly testable, but hints of it might appear in subtle imprints, unusual patterns in the cosmic microwave background, or gravitational effects from neighboring bubbles. If true, it would mean that our entire observable universe, all 93 billion light years across, with its hundreds of billions of galaxies, is just one speck in a limitless cosmic froth. And here's an even deeper possibility. Maybe the universe doesn't just extend infinitely in space, but also in time. Perhaps the Big Bang wasn't the beginning, but just one cycle in an eternal process of expansion and collapse. Some theories suggest universes are born from black holes, each one spawning a new cosmos on the other side. If so, our universe may itself be the child of a dying star in another reality. What then does it mean to ask what lies outside the universe? The word outside may not even apply. Space and time themselves began with the Big Bang. Asking what lies beyond them is like asking what's north of the North Pole. The concept itself may be meaningless. And yet, human imagination cannot help but wonder, When you step outside on a clear night and look up, every star you see belongs to our galaxy. The Milky Way, brilliant and hazy, is just the light of billions of stars too faint to see individually. Beyond them lie other galaxies, millions and billions of them, each with its own stars and worlds. Beyond them lie the filaments and walls, the webs and voids. And beyond even that lies the cosmic horizon, the edge of what we can see. But the universe does not end there. Whether it continues forever, loops back on itself, or multiplies into infinite variations, we don't yet know. What we do know is this: the cosmos is bigger, stranger, and more mysterious than anything we ever imagined. And in the midst of it all, on a small planet orbiting an ordinary star in a minor arm of a typical galaxy, you are here able to ask these questions. The atoms in your body were forged in the hearts of stars and the collisions of neutron stars. The energy keeping you alive comes from the sun, a nuclear fireball sustained for billions of years. You are a part of this vast story, a fragment of the universe contemplating itself. Perhaps that is the ultimate wonder, not just that the universe is vast and beautiful, but that it gave rise to beings capable of noticing.